Hopefully everyone can see my screen now. I am going to tell you a little bit about some of the work we've been doing at Oregon Tech, funded by NITC and supported by the institution here. So we've been developing practical dynamic evaluation methods for transportation structures, as Lisa said. There we go. So give you a little bit more about me. Lisa gave you a good background. I've also been teaching here at Oregon Tech since 2008. Developed 24 courses and delivered all of those. It's been primarily a teaching effort, but as we've been building a bachelor's, master's, concurrent degrees program, I've had the opportunity to develop more advanced electives in bridge rating, bridge design, transportation structures, structural dynamics, and advanced mechanics. And in doing all that, Oregon Tech has a very hands-on focus, so we've been looking at lab components, field components, and lots of demonstration-driven teaching methods. So when I was putting together my first course in structural dynamics, I borrowed a shake table from Oregon State University, and it didn't come with accelerometers, at least not a functional system. And I was looking around for options and realized that my phone had a lot of what I needed. And that was kind of what kicked off this whole effort in using mobile devices to identify accelerations in structures. So we did a fair bit of data collection in that course with the phone, and the results were very good, as good as anything else I had used. So figuring that this was good enough for the lab, I had to wonder if it was good enough for the field. So started doing quite a bit more research just into structural health monitoring broadly, realizing that in general, systems are either created for continuous monitoring of a structure, periodic monitoring every month, every year, something like that, or a one-time evaluation of a structure. And the type of system you might use is going to vary depending on your goals. In general, the goals are either local or global behavior of the structure, or identifying damage either local or globally. So in some cases, structural health monitoring will give you crack development or section deterioration at a very specific location in a structure, and you're trying to identify that very specifically. In the case of the work that we're doing here, it's looking at the global behavior of a structure in order to identify that perhaps damage has occurred more broadly, or just to get a baseline evaluation of the structure. Webb and his team developed a number of SHM categories, which kind of gives the broad spectrum of what people in structural health monitoring are trying to do. On the low end of the spectrum, there's anomaly detection, where you're just looking for a change in the state of the structure, and you might not be looking to identify why that happened, but it may be cause for doing something more. Many studies are just looking at the development of sensors and their deployment and how they're going to function on a structure. Oftentimes, these studies are done in concert with model validation, so an analytical or a finite element model is developed and compared to laboratory or field results. In many cases, if structures are instrumented, they are instrumented in order to identify that a threshold has been exceeded, whether that's a strain level or a stress level. There's something that has happened that is likely to damage the structure. And the holy grail of all of this work is identification of damage within a structure. And if that can be developed more fully, it has real implications for recognizing damage in structures and assessing them. So with that kind of background, the work that I've been doing with a small team of graduate students here is to develop a simple, easily deployed system that generates useful data and ideally generates a very large data set. So a lot of this is motivated by the Cascadia Subduction Zone earthquake that has a likelihood of occurring in the next 50 years, about 30% likelihood. And the expected damage from that and kind of
focusing on resiliency and how we rebound from that event. That definitely motivated me to look at this. And I think the big goal, if we can do it, would be to identify a system that would be easily deployed by a bridge inspection team and that they could incorporate into their existing efforts. So when they go visit a bridge, they have a lot to do. They have a lot to look at on that bridge, but ideally they could also spend 2 minutes with some relatively simple devices and gather natural frequency data. And on a 2-year cycle, if we could collect all of that for all of our state bridges, we'd have a pretty rich data set and could learn a whole lot more. So the learning outcomes I stated for this presentation were to describe the scale of everyday and future hazards facing Oregon bridges. We've got some pretty standard challenges in the state of Oregon. We also have a pretty unique hazard in the Cascadia Subduction Zone earthquake. Want everyone attending to be able to explain, at least at a basic level, the relationship of structural parameters to the dynamic response of a structure. And then I want to give you a framework that we've used for conducting dynamic evaluation of structures in order to find dominant modal frequencies for those structures. Definitely want to give you the results of some of our preliminary field studies. We've looked at ambient traffic and forced vibration, in addition to some periodic jumping with the team of graduate students. And a lot of our data acquisition has been based on mobile devices. So I definitely want you to leave with an ability to use your own mobile device, identify an appropriate app to acquire acceleration data so that you might be able to make some observations of your own. So first, Oregon's bridges. We've got a little over 8,000 bridges. As you can see by the data reflected here, the majority of them were designed and constructed prior to 1974, before the advent of seismic design standards. That being the case, we also have, that means we have a lot of old bridges, and like many other states in the country, the condition of those bridges deteriorates through time, and the state makes a really big effort to maintain their bridges. Right now, as you can see from this, this is from ODOT's Bridge and Tunnel Report 2016, their focus is on allowing some of our good bridges to fall into fair condition while ensuring that our poorer conditioned bridges are addressed. So that's a management strategy that ODOT has taken, and other states in the country may be doing something different. In Oregon, the roughly 8,000 bridges, about 5.5% of them are structurally deficient, which means that one component of the structure, whether it's the deck, the superstructure, or the substructure, has an NBI rating of less than 5. And as you can see in Figure 3 on the right, many states, Oregon's facing budget shortfalls. That means that the money required to maintain our bridges in this condition is likely not there unless we make a concerted effort. So a little bit on the Cascadia Subduction Zone earthquake. There are really two scenarios. There's a full rip, which we've got off the coast here, the Juan de Fuca plate sliding beneath the North American plate. And roughly every 300 years, there's a substantial slip in that fault. It generates an enormous amount of energy. The magnitude of the quake is either 8.3 for a half rip scenario, and 9.0 if the whole fault slips. It's going to result in roughly 3 minutes of shaking and substantial damage to infrastructure, primarily in the western half of Oregon, but certainly throughout the state, and of course in Washington and California as well. That being the case, there's a lot that we can do to try and prepare for that, and certainly the state is doing quite a bit. But as we start looking at designing for probabilistic and deterministic hazards, if we look at the ground accelerations generated by Cascadia or local earthquakes as well, that becomes the acceleration that the ground is going to see. So that's represented here
where we're plotting acceleration versus the period of a structure that might be subjected to that acceleration. As you can see, most medium short span bridges fall in this range between roughly 0.2 and 1 second period. That's their natural period of vibration. And this is just one example of a design response spectrum. This is going to vary depending on where you are in the state of Oregon, both based on the hazard, and it's often adjusted for soil conditions as well. So one of the challenges of this is that bridges are designed based on a natural frequency that's estimated, and the models for estimating those natural frequencies are fairly good, but this quote from Nagayama and his team really says a lot, that while this natural frequency is a fundamental property of a bridge, the natural frequencies of most bridges really remain unknown. So that's something that we can overcome with a simple system. It's a really valuable thrust for some research and some work that we might do. You can also see from this spectrum that if you've got a very short span bridge, so something that is incredibly stiff and its period approaches 0, that the accelerations it moves through are basically the accelerations that the ground is moving through. But as the period of the structure increases, there's this range here, roughly between 0.1 and 0.5, at least in this spectrum, where a structure would have some dynamic amplification. Because of the properties of the structure, it's going to have higher accelerations. And then as we increase the period of that structure, it becomes a longer, more flexible structure. The amplitudes of those accelerations will drop. So again, perhaps fortunately or unfortunately, our bridges fall in the spectrum where many of them are going to be here, where their natural frequency is going to be similar enough to the ground motion that they're going to be designed for the highest possible accelerations. So this is where, if there's uncertainty in the natural period, we'd like to know it, to know that a bridge might not be up here, it might be farther down here. So ODOT's been doing a lot of work on seismic vulnerability, and they've conducted a number of studies. To my knowledge, these don't incorporate the natural frequency of the structures, but more their design details, whether or not girders are going to slide off of bearings, that sort of thing. So these are some results from the seismic vulnerability study of 2009, where under one of the half-rip scenarios, where you've got an 8.3 magnitude quake along the southern Oregon coast, only generating 2 complete collapses along the coast, with a lot of other damage distributed, as you can see, through bridges along these routes. If the quake occurs and the fault slips closer to the northern part, then again at an 8.3 magnitude, you're looking at more extensive damage, but no complete collapses. The Seismic Plus study followed this up with an examination of what could be done and how we prioritize some of the work on bridges, and it's been ODOT's go-to document for prioritizing seismic retrofits around the state. So now to pivot just to basics of structural dynamics. If you've got a structure, oftentimes in structural dynamics, this is the first model you're going to see, where you've got a mass, in this case sitting on a frictionless surface, and it might be forced with this P of T function, so a time varying function. You're measuring displacement of that mass, and that forcing is resisted by 2 things. It's resisted by the damping of the structure that's related to the velocity that the structure might move through. It's also related to the stiffness of the structure, and that is, if the position is changed, there's a resulting force that attempts to restore the structure to its equilibrium condition. With this model, you can generate this relationship that says that the natural frequency of the structure is related to the square root of its stiffness K on its mass M. So that being a fundamental relationship should mean that if we can measure the natural frequency, and we know the mass of the structure, then we can make some determinations about its stiffness. And if we get section loss or other considerations in the structure that might affect its stiffness, those should be reflected in a changing natural frequency for the structure. The natural frequency, at least mathematically, is usually identified in radians per second. If we divide that by 2 pi or 2 pi over that, we get a natural frequency that's more commonly reported in hertz. And then you saw on the previous slide that we can report that in terms of a natural period in seconds. So those are 3 of the same ways of reflecting the natural frequency or natural period of a structure that you generally have to convert between in order to compare results. One of the things that most people have encountered is that when you oscillate a structure, or you vibrate a structure, if you happen to vibrate it at its natural frequency, you get very large oscillations. So many of us have seen Tacoma Narrow's videos, which has something to do with this, but there's a whole lot more involved there. But the idea being that if you force a structure at a frequency omega and it has a natural frequency omega n, if the forcing frequency and the natural frequency of the structure match, you get very high amplitudes. You get dynamic amplification. That amplification is attenuated if you've got substantial damping on a structure. So one of the things you can learn if you can measure the amplitude of oscillations due to a known forcing is the damping of the structure. So some of the other things we might look at, that single degree of freedom model, just a single mass oscillating, is a good starting point. But structures are a little more complicated than that. Most of our masses aren't lumped in one location with a known stiffness. They're usually distributed, they're continuous. So a bridge structure might have a continuous beam, and therefore its mass is distributed along the length, and the natural frequency takes a slightly different form. Still involving the stiffness of the structure, but a distributed stiffness versus a lumped stiffness. Somewhere in between those 2 models is a multi-degree of freedom model. And you can imagine this is a 5-story structure, assuming that the masses of the floor plates are lumped at each level. You could treat this beam in the same way, lumping masses at 5 locations along the length. And you would get this sort of a representation. You would be able to recover 5 modes of vibration. In this case, the fundamental mode has the higher mass. This is an equivalent modal mass and modal height, which gives you kind of a nice way of considering this physically. You try to shake a popsicle that has a very long stick and a very heavy mass at the top. It's going to have a fairly low frequency. And as you go and reduce that mass and reduce that height, you have a higher frequency structure. So that's representative of the modes that this beam might move through, where the fundamental mode, or this half sine wave in mode 1, is going to occur at the lowest frequency. Mode 2 and mode 3 would occur at higher frequencies. So here's yet another look at this, maybe a little bit more physical, where you've got a fundamental mode operating at a lower frequency. Go to a higher mode of vibration. It's going to have a higher frequency, as you can see, and a higher mode still with 3 half waves. You've got a higher frequency still. If you're thinking about this in terms of music, that's probably a good thing. When you pluck a string, it should oscillate in this first mode. If you've ever plucked a string but held your finger right at the middle of it, you've played a harmonic on a guitar, you're forcing this mode of vibration. So there's a good analog between music and the frequencies in music with the frequencies that structures move through. So with all that background, one of the challenges of bridges is that their mass and stiffness are distributed not in very clean ways. So analytical models end up really averaging out a lot of the complexity that we might see in a structure. So one of the best ways of getting the modal frequencies and shapes for a structure is to develop a very detailed model. If you do that, then all of the detail in the model has to be considered. And oftentimes in bridges, we have non-structural components like sidewalks or crash barriers or railings. All of those things that we don't consider to be structural components turn out to have a structural influence. They contribute to the stiffness of the structure. So when we're looking at a dynamic model, we might want to incorporate them. Other things that we have to take into account are soil structure interaction, what happens at the end of the bridge, how it's supported. So the limits of the model to where you cut that model off and apply appropriate boundary conditions become very important considerations. The other thing that happens is we're not just looking at a 2D version of this structure. Its mass and stiffness are distributed in 3 dimensions. So you end up with modes of vibration that aren't just vertical, but lateral as well, and in some cases torsional. The other thing you tend to find, especially with shorter structures, is that the traffic that's on them can really influence their response. So that becomes an important consideration. So just to take a step back into some of the literature, a lot of this work has been ongoing for a very long time. Dynamic testing of full-scale structures really started in California in the early 60s, and conferences were developed where professionals could get together and discuss these things. There are a lot of methods available. Many have been proven very successful, and it's a very hot area of research with a lot of ongoing work all around the world. Most of the research revolves around how you excite a structure, how you sense the response of the structure, and then how you post-process the data and the algorithms you use in order to identify these important parameters. There's certainly consensus that structural health monitoring can support performance-based design, and that we can use it to consider how we manage our infrastructure assets. And I think one of the big takeaways from this paper by Aktan and his team is that the dynamic test of a constructed system should therefore be executed with a careful evaluation of observability, repeatability, and the system of interacting elements in the engineered structure, the nature and the human. So the challenge in this work is that you've got a lot of variables that might change the parameters that you measure. And that's like any experimentation. These folks call it out very clearly. This is a bit of an eye chart, but one of the things that Aktan put together was all of the parameters that you might need to consider in developing a system. So the design of your test, the inputs, the system itself, its outputs, how you process the data, the properties you're trying to measure, the analytical model you might be comparing to, the parameters that you're getting from that model, and then verification. And this truly is a cycle, because once you develop a model and go out into the field, you realize that that model maybe didn't give you the best results, and you have to tweak it. One of the other takeaways from this paper by Aktan is that the global relationship that should therefore govern the design of any field test to ensure success is illustrated here, that you've got a relationship between the model you're using, the experiment you're conducting, and the observer. So as we're trying to develop a system for bridge inspectors, we need to take into account their background and what they might be looking for in a structure. So a little more literature, maybe a little more focused on mobile devices. There are a number of papers where people have attempted to use the accelerometers in mobile devices in order to get response data from structures. In many cases, it's in the lab, and in most cases, the papers compare lab results to some kind of a field study. So Morgenthau and Hallerman found modal properties for a laboratory beam with an array of HTC Legend mobile phones. Hofner and the team there evaluated a series of mobile devices using a shake table and an iPhone 4, and they found good agreement at low frequencies, around 1 hertz, but they saw that there was degradation of the measurement above 8 hertz. They said they were working with an iPhone 4, but at least in this data, they didn't identify exactly which device they were using, and they did have a number of devices identified in that paper. Other folks working with iPods. A group in China is testing light poles by using an iPod attached to that pole, and then this fellow is striking the pole in order to oscillate the pole. They found stability of the frequency of the pole over a matter of days and in varying environmental conditions. And then they did find after 2 years that there was a frequency reduction in the pole, but they didn't identify exactly what that was. So this would amount to an anomaly detection sort of study. A paper that came out relatively recently and looks a lot like the work we're trying to do is another team out of China. Actually just discovered this earlier this week and haven't had a lot of time to look into it, but it looks incredibly promising. They have an app called Orion CC, and it's available to document structural health monitoring experiments, both with accelerometers from an iOS device and video shot from that device. So you can see on the left, they're generating a frequency response spectrum from accelerometers. On the right, they are taking video of a moving dot, in this case on a tensioned cable, in order to identify cable forces. They found that they were able to do that with both methods, and so it gives us a good basis for pursuing and continuing to pursue the work that we are here. So now to some of the tests that we've done here. Again, a lot of this was developed out of coursework that I've been doing here. And so I developed a simple lab module to expose students to damage detection. So we took a 2x4 cantilever, placed a phone on the tip of that, considered the stiffness of this cantilever, and a lumped mass applied to the end of that cantilever. We found the natural frequency, in this case the natural period, 0.22 seconds, and then we inflicted section loss at 1/4 here near the support, and then 50%. And we did see an increase in the period. So with a softening of the structure, you get an increasing period. So that's generally what we're looking for in this sort of work. Other things we've done is compared the results of iPod measurements to those from an instrumented impact hammer, which is a common method of doing more sophisticated studies, but one of the results from it is the fundamental frequency. This is a concrete T-beam at Portland State University, and this is Thomas Schumacher, one of our collaborators there. So when we get into this, methods of excitation become important. You can use either ambient traffic, use something like the impact hammer that you saw in the last slide, or if we get out into the field, one of the common, very easy methods to employ is jumping in unison. You just get a group jumping on the structure. You get periodic impact from that jumping, and then the structure itself oscillates and damps out. And so from that, you can get frequency response and look for dominant frequency of this natural oscillation that's occurring. The other thing you can do to get better results is employ forced vibration. You employ a harmonic forcing, and now you've got a known frequency of vibration that you can try to match with the natural frequency of the structure. And when you're testing at resonance, that generates not just confirmation of the natural frequency, but also an ability to identify the damping parameters of the structure. When we looked at methods of sensing the response of the structure, again, we've been focusing on mobile devices, compared them with conventional accelerometers, and there are a number of apps, a couple of them listed here. I've got a few more on another slide. But these apps basically take the accelerometer that sits roughly in this location in an iPhone or an iPod, and it gathers that data roughly on a 100 hertz sampling rate, and depending on the app, you can get different results. The other thing we're looking at is some non-contact sensing, similar to that group in China. we're working with something developed, again, by Thomas Schumacher and Ali Shariati at Portland State University. They're calling it the virtual visual sensor. And it's a relatively simple means of taking video of a target and looking at changing intensity of a pixel across this boundary, this black-white boundary. Changing intensity in the video can be correlated to the natural frequency of whatever that target is attached to. And indeed, they've found that you can look at edge pixels. So something like right here on this railing might also be a sensor. The benefit of this method, and something we'd like to continue researching, is that every location on the structure then becomes a potential sensor. You don't have to worry about wiring or developing a wireless sensor network with a number of devices. And so we're working across these two methods in order to validate both. So in some of the work that we've been doing, we're shooting 60 frame per second video, 720p resolution, makes for kind of a happy medium, and we're able to get frequencies up to 30 hertz from that. There are a lot of precursors to this kind of work. There's machine vision, close range photogrammetry. Others have come up with blurred image methods. So again, there's a lot more research to support this sort of work. Said I would talk a little bit more about the apps that are available. My current favorite is one called Vibration Analysis. It's on the Apple App Store. The nice thing about it is that it generates a frequency spectrum that includes the amplitude and the frequency at the peak. So you get very clear results immediately. This app, like many of them, has an email export, so you can export both the time history, the acceleration through time, as well as this frequency spectrum generated by the app. This also has screen capture, so it allows you to take these pictures and put them directly into your photos. And it has adjustable units, an FFT window, and there's actually a lot of other functionality. It can work with Bluetooth accelerometers and can do much more. But so far, we're focusing on the accelerometers within the device itself. And I mentioned Orion CC with that group out of China. That's certainly something I want to explore more, because it seems like they're pursuing the same sort of thing. A lot of other apps that have attempted to do this are currently out of date. These apps seem to be developed, used for a few years, and then the developers don't update them, and they fall out of favor. This vibration analysis app seems to be continuously updated right now, which is very nice. All these have different capabilities, and a number of them can broadcast the data that they're collecting via UDP, so via a Wi-Fi signal. There's a little bit of work to turn iPods into a sensor network, but that's another thing we've been pursuing here with not a lot of success, but the potential still seems to be there. And if we look at just the output from that vibration analysis app, the amplitude of the peak acceleration at a frequency is identified, so you can see that. You get the dominant frequency itself. And then in this case, you see some of the harmonics and the higher modes showing up. Some of my graduate students have been doing work to confirm the frequencies that we identify with iPods. So we've got a conventional accelerometer with this Quanser shake table. And you can see here that the Quanser shake table accelerometer, this is a limit on identifiable frequencies. So if a frequency is very low, like some of the ones that we're trying to measure on civil infrastructure, you have to have fairly high amplitudes in order to measure that acceleration. So these were tests in order to identify the boundary and where we just might not be able to identify a frequency. You can see that the Quanser accelerometer has a bit more range, so better accelerometers generally get a better ability to identify frequencies even at low amplitudes. And the other thing that's here is some of the virtual visual sensing. So we also shot video at various distances and various resolutions. And the nice thing about the virtual visual sensing, you can see here, its limit is not frequency dependent. It's dependent on the distance of the camera from the target and the resolution of the video. So that means that with these two methods, we actually have a way of identifying frequencies across a very wide band. Some of the other fun we've had, once you have a lot of iPods running the same software, you can basically treat them like a sensor network. I've got accelerometers in each one of these. This was a yardstick that I'm oscillating. The peak amplitude shows up here, and if I plot it, I can recover fairly closely that half sine wave of the first mode of vibration that we're looking for. And you can see that all of these share the frequency, the natural frequency of that yardstick. So with all of that, we decided to go out to the field, fairly confident with our devices, and we're looking here at a bridge. It's a fairly short span, 28.7 meter bridge. It's got a very high skew. It has integral abutments, and it's a composite steel girder with variable flange thickness. Had good access, good sidewalks that we could get out onto, and you can see here we're shooting video on a target there, and then we also have some of our forced vibration happening there. Forced vibration required us to build this shaker frame. You can see here we're driving a very specific mass at a specific frequency, and that allows us to vibrate the structure and look for this natural frequency. The frame itself is very heavy, so that the shaker forces are transferred directly into the structure. The dynamic force is being supported by this tie rod and the armature of the shaker. And we did a fair bit of work to get the shaker into an equilibrium position using these bungee cords. It takes a lot of them because the shaker body weighs 78 pounds. That gives us a pretty good dynamic force that we can apply to the structure. The shaker limits basically prevent us from driving the shaker too hard, requiring too much power to do it. So we've got at a maximum for this shaker a 30-pound dynamic force. We probably ended up with more like a 20-pound dynamic force. And you can see sort of our setup here. We've got a laptop driving the shaker. Active control is possible, but we don't have an accelerometer providing active feedback to this. But the potential is there, and we're going to move in that direction. So as we're shaking, we've got an iPod there on the deck, and we're basically looking for that frequency spectrum, and we can force this at frequencies adjacent to what we think is the natural frequency, watch the amplitude of response fall, and be fairly confident that we've identified a natural frequency for the structure. The model that one of my graduate students developed was a finite element analysis model, very detailed, using plate elements for girder webs and flanges and the concrete deck. It's done in Midas Civil. The goal for this is to find the antinodes, or the locations of maximum amplitude on the structure. So that those would be locations where we would both excite the structure and try to measure response. One of the things we realized is that we did need to incorporate the sidewalk into the deck. There's rebar detailing that connects these two elements, and so once we had added that sidewalk in as a structural component of the deck, we actually got fairly good results. So the modal analysis of that structure gave us a frequency in the first mode of right around 4 hertz, the second mode about 11.5 hertz. And this is in plan view, the red identifying the locations of maximum amplitude. We take our team out there, do some periodic jumping on the structure, and measure the response with the iPod. We were able to identify a frequency
which looks a lot like this dominant mode. So we measured 4.17, 4.07 in our model is pretty good agreement. Less than 3% difference is significant. We also identified 11.42 as a second mode of vibration, and compared to the 11.64 in the model, looks like pretty good agreement. And we used the video and the virtual visual sensor, and we were able to identify some frequencies in this 4 Hertz range. There's a lot that can throw off those measurements. We were in a windy environment. We were still able to identify these frequencies. So it seems like the VVS is going to be a good method to continue pursuing. As you go up in frequency, you go up in these mode shapes, and you get higher frequencies, you get wilder modes that might be present but might not be very strong. Get into still higher modes and you get all of these very interesting shapes that we're probably not going to be able to represent. One of the other challenges early on in the model was we saw these lateral torsional buckling modes of the girders themselves, and that was an indication to us that we didn't have the cross frames properly connected to the structure. Once we addressed that, our model got much better. So future work, we want to keep working on our procedure, streamline it for implementation by a bridge inspection crew, do more field work this summer, and keep following the literature. And we hope to see a whole lot more. So I think that's it. Happy to take any questions at this point.
All right, great. Thank you, CJ. For those viewing the webinar, please feel free to continue to submit your questions if you have them. Go ahead and take a few questions here to start. So Chris or CJ, for the accelerometer application that you used, was there any calibration that you had to do prior?
No, there's not any calibration on it, and that was one of our concerns, is that we didn't have a ground truth, so that led us to put the iPods onto a shake table, force at a known frequency, and ensure that we could identify that frequency.
Okay, and a few more questions on the bridge that you selected in the exercise that you did. Can you discuss how you selected the bridge that you tested, and did you confirm any degradation prior to testing?
That's a good question. The bridge, it's mostly a practical consideration. It's relatively lightly trafficked, has these big sidewalks, so we can access it easily. When we did go out to do the forced vibration, we got a lane closure so that we could operate towards the middle of the deck. That allowed us to test with both ambient traffic and with our forcing system. So that meant that we could get some pretty good results. We weren't looking for damage in this structure. That's something we'd like to do, but in this case we were really just trying to get some proof of concept, more of a feasibility study that we could use the iPods in order to generate some good results, and that we could also use the virtual visual sensors to confirm those. So that damage detection is definitely the holy grail, and I have hope in the future that we can identify a bridge project where they might be making a repair, where we could evaluate the structure prior to repair and then after, and kind of identify damage in reverse.
Great, that'd be very interesting. So for the technology that you used, do you foresee any issues using the iPods as technology changes or as new versions of technology come out?
Yeah, it's definitely a problem. As I mentioned with some of those apps, some of them like Seismometer and iSeismometer we were using 2 years ago, and they're not updated anymore. You can still download them and put them on your phone, but they may not work very well with updated operating systems. So there is that challenge. It's especially a challenge since we're not controlling the app that's doing the work. Just tried to rely on other work that people are doing.
And you can see that team in China is basically developing their own app, and that's probably a direction we should go if we're going to have control over that.
Great. Okay. And you did mention some of your future research and future steps. What do you foresee as your next projects, and how soon do you think that might be something that practitioners would be able to use in their investigations?
Sure. So with some of our field work, and as we get more comfortable with these systems, we're trying to develop just a one-pager, basically instructions that somebody could use to take a mobile device out to a bridge, set it down, watch a changing frequency response spectrum in order to pick up some dominant frequencies. So it would really be driven just by observation. And the goal is to try and make this a system that could be implemented relatively easily. You don't have to go out with a lot of equipment. It's just a mobile device and a person with some experience watching a changing frequency spectrum so that they could collect those dominant frequencies and put them into a database.
Great. Well, that will be exciting once that's ready for dissemination.
Yeah, it should come out this summer.
Okay, great. So we have another question here. And how easily could this be adjusted for buildings and other structures?
I think very easily. Really anything that vibrates. The vibration analysis app was actually created by a mechanical engineer looking at fan speeds and that sort of thing. So the applications are really up to anyone who cares to put their phone on something. And you could use this for studies of floor vibrations, use it for studies of light poles, really any structure.
Okay, great. Well, that actually wraps up the questions that we have. If there's anything else, CJ, that you wanted to include for any final comments or thoughts?
I'd just say if anybody's interested in being part of this or talking with me more, feel free to reach out. I would look forward to more collaboration, and we're going to have more collaboration with Portland State University in the coming years. So I'll look forward to that.
Great. Well, thank you, everyone. This concludes our webinar. Thank you for joining us, and thanks again to CJ for sharing his work. You can view other professional development offerings on our website at nitc.trek.pdx.edu. All right, enjoy the rest of your day.